Our next speaker is Richard Vidal. Richard is the director and executive vice president of a Renaissance Gold, a publicly traded junior exploration company focused on the Great Basin, USA. Along with Ron Parrott, Richard was a co-founder and executive vice president and director for OX Ventures Incorporated, responsible for the large off-trend discovery in Nevada, known as Long Canyon. Richard has over 30 years of exploration experience, including an adjunct faculty position in exploration geophysics at the McKay School of Earth Sciences and Engineering at University of Nevada in Reno. Previous work experience include Homestake Mining Company as part of the global target selection team and managing the technical group for exploration, and as an exploration geologist with BP Minerals and Rio Tinto. Richard is a recognized expert in remote sensing and geospatial technologies and was the lead editor for the 2009 Society of Economic Geologists publication on remote sensing and spectral geology. Richard.
Thanks, Jiaodong. So I'd like to acknowledge my co-authors, Benoit Rivard, who's professor at University of Alberta, Dave Browning with Terracor, and Mark Kulbach, chief geologist at Renaissance Gold. So just to start, the thermal's important because it can map silica and silicates directly, the framework of the Earth's crust. And this here is a diagram made by Phil Harris, president of Terracor. We saw it earlier in some other talks. Here's the family of minerals. Here's the visible to near IR response, the short wave response, and then lastly, the long wave response. And we'll get back to that to discuss specific deposits. So what we've been looking at is reflected energy in the visible and shortwave infrared. This is the energy emitted from the sun as an idealized black body at 6,000 degrees Kelvin. And it is no mistake of evolution that the human visual system has optimized that energy output for what we detect. But what we're interested in for thermal is way out here. This is the 300 degree Kelvin black body curve, which approximates the energy being emitted from the Earth. So you can see there's a lot less energy out there. And in addition, we've got the transmittance table. If you're doing remote sensing, the energy is blocked in these areas. A lot of the work in the thermal has been basically between the 8 to 12 micron area. So this is a simple cartoon showing the sun with incident energy upon the Earth and reflecting off a rock, and that's what we've been talking about through the beginning of the session. But what we're interested in is the energy that's absorbed and re-emitted. And that gets down to Kirchoffs Law, where the emission is proportional to the absorption for a given wavelength. And this is what allows us to detect different types of silicate mineralogy. This is an old plot by Lyon and Green from '75. And you can see here there's a whole bunch of different rock types here. But most importantly, we see a shift in the major absorption feature from framework silicates. And as those bonds become less and we go to sheet silicates, chain silicates, bow tie silicates, right down to individual silica tetrahedra, such as an olivine, there's quite an extensive shift progression. Anyway, this here's a table, which I don't expect you to read. It's in the publication. But the key is that this is some of the more important sensors that have been used in mineral exploration. We went from single band Landsat imagery, which wasn't that useful. And then we've gone down to multi-band imagery, the most useful of which is Aster, and we'll show you an example there where there's 5 bands coming off a satellite. And then there's some multi-band airborne systems, which have been used a little bit, but not very extensively. And then we're getting down to the hyperspectral imagers, such as CBAS here, and I'll show you some examples from that, but also these detectors such as the Spectrum Owl, which I'll talk about, and there's the HiLogger 3, which I'll talk about. So this here is an Aster example, And here's the visible to near infrared, shortwave infrared, thermal infrared. And with the aster band shown along here, you know, there's more energy in this part of the spectrum, so the pixels are 15 meters. There's less energy out here in the shortwave infrared, so you need a bigger sample if you want to have more narrow bandwidths. And out here in the thermal part of the infrared, they had to have 90-meter pixels in order to get enough signal to noise. And this here is an example from Nevada. This is a project we worked on at Renaissance, and we can see a geologic map here. And here the aster is doing a pretty good job at distinguishing between lithologies. But importantly, there's this thrust up here, which is just riddled with massive quartz veins, and it's really highlighting that quite well. Okay, another feature I wanted to talk about, this is highly underutilized. You know, rocks have different thermal properties. One of them we talk about is the diurnal variation, and that's between looking at the difference between like a daytime thermal image and a nighttime thermal image. And some rocks retain heat longer than others and give it off slowly. Others get rid of their heat pretty quickly. Well, this is pretty cool. You can take a single broadband thermal image and fly it pre-dawn, and you can see quite a contrast. This is not absolute data. This is all relative. But what you can see is you can see like siliceous rocks here. You can see, due to variations in soil moisture in the pediment, you can actually see buried fault systems. And you can also see outcrops at depth. I actually drilled a target in Nevada where I found an anomaly out in the pediment, drilled it, and it was 30 meters deep. It was there. So that's something that hasn't been used much in mineral exploration, but maybe should be. Okay, master. Sorry. Huh. Those images aren't on there. Interesting. Anyway, this was a great paper by Simon Hook at JPL. And I'm sorry I can't show you this. This is an airborne system. It was developed to test aster data, but instead of 5 bands, they had 10 bands. They just put them together to kind of simulate what aster might see once they launched the satellite. But an important thing of what Simon did here is he correlated silica content of rocks with whole rock XRF. He actually has a silica abundance map. And this has been done before. Chuck Sabin did a PhD at Mackey years in the 90s and mapped intrusive rock types in the Desolation Wilderness using some of these multi-band thermal detectors. Okay, and this is sea bass, and the late Jim Terracor at Mackey did a tremendous amount of thermal work, and this here was just done for a class project whereby they took it out to Death Valley and they just imaged this outcrop here. And you can see a lot of variance in the thermal part of the spectrum. And this is related to the amount of quartz in those units, as well as carbonate and other unknown strata. But very expressive lithologically. We'll see some more detailed examples of this. Now, CSIRO has been a real pioneer in the thermal part of the spectrum. They've done some great stuff. Lou Whitbourne, their physicist, developed an active laser thermal profiler that could be flown, and really cool stuff. And this here is a paper by Tom Cudahy in 2009 from that SEG volume we put together. And this is in an Archean gold system with gold on this axis here versus downhole depth. So you can see this interval in here highlighted is rich in gold. And these other plots show what was derived from TIR logger. It's a profiler. And this is quartz content here. This is plagioclase content here. And this is carbonate content here. So this was some of the more important early work with thermal imaging for core scanning. And then last year, that didn't come out either. Anyway, there's a paper published last year by Green and Shadlock using the high logger 3. And this is a great paper because it shows cation substitution in the carbonates that you can't get in the shortwave infrared. In the shortwave, you can map calcite, dolomite. but to be able to look at specific iron manganese species like cutnahorite and rhodochrosite, you can get tremendous discrimination in the thermal part of the spectrum, and that was for volcanic-hosted massive sulfide in Tasmania. If you look at the work Jeremy Vaughan published in Economic Geology on carbonate cements in Carlin systems, that shows that this is the kind of information that's quite important for Carlin systems and other sedimentary hosted deposits. Oh boy, where did these? Can you see that image on your computer? Whoa. All right. Anyway, this is an example from the University of Alberta from Benoit Rivar's lab and his PhD student Michelle Tappert. They published a paper in 2015 using both long-wave infrared and short-wave infrared. And what they did is they created classifications related to dilution in kimberlite. As has been shown by previous speakers, there's a tremendous amount of data embedded in here, and you kind of have to domain the data and classify it to be useful for production and looking at ore deposit models, etc. You go nuts putting this into mine scale drill data. So they made classifications based on kimberlite dilution. And of course, that's really important because then you can see the amount of dilution. You can break it into different compositional types, what that diluted host rock is, and that determines processing. Which metallurgical stream does it go into, or does it just go on the heap and not through the processing circuit at all? Okay, now we're down to Terracor, which is the only commercially available imaging thermal system. And they use the Spectrum Owl with 84 bands, and they run it at 2 resolutions, at 1 micron pixels and 0.4 micron pixels. And the high resolution one is being run at the ALS Oil and Gas Lab in Houston. And the petroleum people really like it because you can really pull out very detailed textural relationships there. To do a scan of this core, including the visible, the swirl, and the thermal, it's 3 minutes per box. It's literally 1 minute to scan it, but 3 minutes is the production mode because you're taking boxes off and on, you're keying the box number into the computer, this kind of thing. They did 230 kilometers for the Swedish Geological Survey, averaged 1.5 kilometers a day. Visible, near IR, SWIR, thermal. So if you go with the higher resolution, it takes about double the time. And they have a range of instrumentation too, from this desktop system, which is sold by Spectrum, to Terracor's designs of this mobile system, which is a 2-headed system. It's lightweight. You can put it in a chopper, set it up in a remote drill camp, set it up and have it calibrated in a day and be producing core scan data very quickly. And this is the 3-head facility. Oops. 3-headed facility here, so you can put on 3 systems here. And of course, going into the mobile environment, what's really going to happen is companies are going to want to scan pit walls and mines and this kind of thing. So again, it's useful from exploration right through to production, life of mine, as Dave Coulter eloquently put it yesterday. So I'm going to give you a quick example of a reduced intrusion gold system in Nevada where there was a master's thesis on a Renaissance gold project. And most of it was drilled with RC, but there were a few core holes. Terracor scanned this for the university as part of the thesis. And it was an interesting one because it went through some anomalous mineralization, and it's got a whole variety of alteration types of different ages. There's skarn, there's hornfells, there's albertization, there's propylitic alteration, and interestingly, there's borosilicates of schorl and axonite. So this here is the Intellicus software. We can look at your downhole geochem. And what they do at Terracor, instead of going directly to a library, they do a self-organizing map, which is a classification to just look at the dimensionality of the data spectrally. There is so much information out there. Don't pre-guess what you might be finding. So it breaks it up into initially 20 groups on a single core. So you just scroll down, you see where there's anomalous gold, and you go, oh, there's this orange color that seems to come up whenever I hit gold. So look at it, and you say, okay, it's got quartz and tourmaline in it. And so then you can do a feature extraction specifically for that mineralogy. And here we're looking at a close-up of quartz tourmaline in here, and this is a micrograph about 11 millimeters across, showing the intergrowth of shoal quartz and sulfides. So very quickly you can determine what's important. Okay, here's another example of doing slabs for Dave's thesis. Patrick's thesis. And this here is the quartz signature coming off the scanner on that pixel there. And this is the quartz reference. Down here, we've got tourmaline coming out, which of course is a shortwave infrared feature. And this here shows work from Patrick's thesis whereby he's got an SEM backscatter image with K-spar and quartz on this specimen. And here we're getting the quartz and K-spar in the thermal spectra. And here's a photomicrograph off the same specimen showing chlorite. And that's where the chloride is there on the specimen in the thermal. Now this is interesting. This is just a false color composite. And the yellow is indicating it's silica rich. But there's a difference in the tone between where the mineralization is versus the siliceous metasediments. And so it's an important thing to realize we're getting more information out of here than just pure mineralogy. That gets into spectral petrology that Brigitte talked about. We can also look at specific chemistry, grain size features. There's a huge literature in the planetary sciences, and this is kind of summed up in the paper, and crystal orientation information. So Tom Cudahy in 2001 published on plagioclase cation substitution. Again on garnet cation substitution in the thermal at the famous Urington Porphyry in Nevada. And then in the planetary literature, there's some information here on olivine and the iron magnesium cation substitution, in pyroxenes, and as we would have liked to seen in the Green and Shadlock paper in terms of carbonates. So we're down to much more fundamental vibrations in the crystal structure, and we can derive a lot more information in the thermal than shorter wavelengths. And there's a bunch of information on grain size, but most importantly, there's an increase in absorption features with decreasing grain size. But in the thermal, because we're dealing with longer wavelengths, there's a theoretical limit of 3 times the wavelength to dependably use this spectral information. And so if you're looking at 12, 13 micron features, once your grain size gets to 40 microns or so, you've got to start wondering whether what you're seeing is actually correct. And of course, in optical mineralogy, there's a tremendous literature on anisotropy. It's one of the basic petrographic tools that has been used for over 100 years to do petrology. And you can really see some information in the thermal part of the spectra. This here is a paper by Benoit Rivard and his graduate student, Michelle Tappert, looking down the C-axis of quartz veins versus an A-axis. And you can actually see distinct spectral shifts related to the anisotropy of the crystal. And here's a great slide. This is by Dave Browning in a paper he published with Toby Kasanke, using the high-resolution thermal scanner at ALS Chemex, and he presented this last year at the Geologic Remote Sensing Group meeting. And there's a distinct difference here in the spectrum between calcite grains and calcite cement. This has the petroleum people very excited, and people who study Carlin systems are really keen on using this kind of information. So, not just alteration, but gang mineralogy. We can actually map mineralization. And in the paper, I go through a number of deposit types and explain what thermal can do. I'll just show you a few right here. Mafic magmatic deposits, nickel, copper, PGEs. Fractionation's very important. What controls the sulfur solubility in a mafic melt is the iron content. So knowing the cation substitution in a layered mafic complex is absolutely critical to finding ore, and this can only be done in the thermal part of the spectrum. Porphyries, you can do a lot with shortwave, looking at fengite micas versus muscovites and this kind of thing, but in porphyries we can image feldspars and quartz directly. And with skarns, calc-silicates, Larry Meinert summarizes the families as garnet, pyroxene, olivine, and peroxenoid. And again, this is best done with the thermal part of the spectrum. But you can also get information on feldspars, carbonates, and phosphates. And with epithermals, there's a vast literature in the high and low sulfidation literature. But when you can map things like quartz adularia directly, that could be quite important, not just for finding it, but for defining metallurgical circuits and actually modeling the ore when it hands off to the engineers. Volcanic massive sulfides, plagioclase, olivine, cordierite. Up in the Abitibi, they have headframe rock or dalmationite. It's just rock riddled with cordierite. And of course, carbonates. So, in summary, it's not just alteration, but gang that you can map. Silicates obviously are critical. They're the framework of the Earth's crust, the most abundant mineral family out there by far. And of course, we can get superior information with carbonates. We can map phosphates and dark minerals. There's a number of projects that have been hampered trying to do spectral work on dark rocks. You don't get enough signal to noise to be able to get useful spectra out. And the thermal doesn't matter because it's emission, it's not reflection. Pre-dawn thermal has some depth penetration, unlike the shorter wavelengths. And probably the key feature is cost. Thermal is not cheap. To have a thermal detector of any use to mineralogy, it must be cooled to get sufficient signal to noise. So it's a lot more expensive, but the costs are coming down rapidly. And I dare say this is going to be a very important technical gain in use in mineral exploration over the next 10 years is the thermal part of the spectrum. Thanks very much.
Since we are running over time, I'd like to conclude the session, but invite questions for all speakers. If you, since we have the room available, Richard.
Yeah, that's fine.
Any questions for Richard or any previous speakers? Well, go ahead. I'd like to ask Ray to address that. What technology can deal with the vegetation?
Actually, I'd like to comment on that. If you have a very high signal-to-noise remote sensing system, it's shocking how much you can see in wooded areas. Because if there's enough in the soil or that just is a bit exposed, I mean, up in Alaska, I've imaged effectively to way down into the valleys, not the cores of them. But it's amazing, you know, you think you're not going to get a signal, but you can if you've got very good signal to noise. Get something of interest.
Other questions? If not, I'd like to thank all speakers. Please join me to thank them again, and thank you for coming. I hope you enjoy the rest of the conference.